It's a great pleasure to be here, and really nice to see so many young people who are interested in this area, or at least wanted a day out, which is always good. What an inspiring talk we just had, really fantastic. And I think, thankfully, that's going to introduce a few of the topics for my talk. I'm going to be telling you about another laser-based technology, and this technology is able to make the shortest events that we know in nature, and certainly the shortest that we can control. And there are very close connections to accelerators, which I'll mention, but also what's really interesting is that the next generation of accelerators are actually beginning to look like they're going to be able to get into this regime of attoseconds. So let me kick off, starting with an obvious fact that technology really improves our ability to observe the world around us. And a great example of that, if we go back to the 1600s, Galileo with his telescope. He made his own telescope. It had fairly modest magnification of 20 times. And he pointed it at the skies. I'm not sure whether he had a little peek at his neighbours first, but he pointed it at the stars and he observed this. Now, does anybody know what this is a picture of? I heard somebody say Jupiter. Very good. And the little asterisks that he drew, this is his own drawing, are the four Galilean moons, as we know them now, Io, Europa, Ganymede, and Callisto. So with this primitive, by modern standards, technology, he made a really remarkable discovery that could not be observed with the naked eye. So this is an example of technology boosting our ability to see and to observe what's going on around us. And I think he would be absolutely blown away to think that in the 20th century, people were actually being sent to the moon. Now, what about if we want to observe something that's not distant, but moving really fast? Now, one of the limitations of our eye is that we have something known as persistence of vision, which means that we basically have this after image, which lasts about a 25th of a second. And so we can't really see or detect something changing on a timescale less than that. And so we have a very fundamental biological limit. Now, obviously, we've got technologies around us that have been developed to enable us to capture faster motion. And a nice example of that is back in the 1800s, a guy called Muybridge developed a camera shutter which enabled him for the very first time to make photographs of a horse galloping. And he was trying to answer the question as to whether the hooves of a horse leave the ground at the same time, because with the human eye, it's actually not possible to really see whether that's true or not. And indeed, he made the first kind of image of that and actually did prove that the hooves of a horse, when it's galloping, are all off the ground at the same time. Now, that technology looks very primitive. It's sort of brass and wood, and we'd expect to see it in a science museum. But the important thing is that at the time, that was cutting edge. That gave the fastest shutter speed that was available at the time, and it led to a new discovery, in this case, to do with a galloping horse. But he did a lot of other interesting stuff to do with biomechanics. Now, nowadays, we all have phones, and we use digital cameras, and you may have played around with a shutter speed on such a camera. And I did a simple little home experiment with my daughter here, Lucy, who was, she's a bit embarrassed by this picture now because she's now a GCSE student and she doesn't like people seeing her running around in her pajamas. But anyway, did this in the garden, and what I did is I changed the shutter speed from 1/4 of a second all the way to 1/250th of a second. And the key point here is that to capture some fast motion, in this case her running, to get a really nice crisp image where nothing's really moving on the timescale of the exposure, I really needed to get to about 1/250th of a second, which is down here. Because you'll see that even at 100th of a second, there's some blurring. I hope you can see that of her hands and feet. Now, just to sort of set a little marker in the ground, some of you might even recognise this kind of shutter controller shutter speed controller on an old SLR camera, and the numbers here represent the shutter speed in 1 over this number. So when it's set to 1,000, it's 1,000th of a second. So I'll just bear that in mind. So I would have had this. I didn't use such a camera, but I would have had it at the 1 over 250th. I did it on a digital camera, but the same idea. So the take-home message on this point is that if it moves very fast, we're going to have to measure it very quickly. And that's also going to apply when we want to look at things like electrons. Now, short flashes of light from lasers actually can freeze motion faster than any shutter. And there's a long history of people being interested in using light to do that. If we go back to the 30s, Harold Edgerton, he developed flash lamps that could produce like strobe lights, very fast bursts of light. And he was able to illuminate something that he wanted to watch with one of these strobes in a darkened room and use a camera with its shutter open, so the exposure was made just when the light was on. And with that, he was able to get down to microseconds, so 10 to the minus 6 of a second. And he made some really iconic photographs, many of which are sort of almost in the public domain now and familiar to us all. One of my favourites is the picture of these balloons that he captured very shortly after being burst with a bullet. So if you look closely here, you can see a bullet. And what I find amazing is that with this 1 microsecond flash, he was able to capture the bullet pretty nicely in flight. Another really fascinating thing is that that bullet has travelled about that far, and already on that timescale, that first balloon is totally shredded. So that's just a really interesting thing. And we'll see actually that this is a little bit like a pump probe experiment, but this is the kind of things that he was able to do with his technology of the 1930s. So let's think a little bit about the key kind of point in this, and that is, what if we want to try to understand what's going on, not with balloons, but with molecules. Now, obviously, balloons are interesting to 5-year-olds, but for the rest of us, perhaps a molecule is a more interesting system to study. Now, let's take this molecule, and we're just going to apply fairly basic physics to try to work out how fast we would need to make a measurement of that to actually witness, for example, this atom flying off. So the first thing we could do is to calculate the acceleration using F equals ma again. And it turns out that if you put the Coulomb force and the appropriate mass into this, you get an acceleration in such a event, a dissociation event like this, of about 10 to the 14 to 10 to the 18 G. Now, you probably know that fighter pilots, they sort of black out when they get 5 to 10 G. This is 10 to the 14 to 10 to the 18 G. That's what that atom is experiencing in terms of acceleration. Now, another simple equation, if we want to work out, given that acceleration, given a certain distance it should travel, we can work out how long a time it would travel. In this case, I've taken a distance of about 10 to the minus 10 metres to sort of be separated from the molecule. And if you work it out, that's about 1,000 to 10 femtoseconds. That's how long that atom takes to move. And just to remind you, a femtosecond is 10 to the minus 15 of a second. So what we already can learn from this very simple analysis that I'm sure all of you could do is that we would need a femtosecond light pulse if we wanted to not look at balloons or horses, or my daughter in fact, but at a molecule breaking apart, and to try to make some blur-free, in quotes, exposure of that. Now, what's happened is the development of very short pulse lasers, known as femtosecond lasers. You can go off and buy one of these if you have a spare couple of £100,000. And the basic way we can make measurements of the kind of things that I've been talking about, basically atoms flying apart, is to use something known as pump probe. Pump probe is a very elegant technique where the femtosecond laser is split with a beam splitter, and we make 2 beams. One beam, the red beam, excites some dynamics that we're interested to look at in the sample. The blue beam, known as the probe, comes in at a certain delay afterwards, and it interrogates, in other words, it interacts with the sample, and we can learn something from the way that interacts with the sample. And if we repeat the experiment many times, changing the time between these 2 events, we can build up a movie of the interaction or of the excitation. And using this exact idea, Ahmed Zewail, who unfortunately died a couple of years ago, he was able for the very first time to look at exactly the kind of system that I mentioned before, basically a molecule flying apart. And he did that with a time resolution of a few hundred femtoseconds. And he for that, he very deservingly won the Nobel Prize in Chemistry, which I guess is better than nothing, but that was what he got. And this was for the studies of transition states of chemical reactions using femtosecond lasers. So I had the fortune to meet him once, and it really was a huge event in our ability to look at very fast events, but now on a very small scale. Now, that was atoms moving apart in a molecule. Could we imagine actually going in another layer and making a movie of electron motion? In other words, the little electrons that are whizzing around, e.g. in bond formation. We know that when a bond is formed, ionic or covalent, we have electrons that are moving very quickly. How short a pulse would we need? I guess our gut reaction would tell us that it's probably going to need to be shorter than it was to see the larger structures. Now, if we cast our mind to the sort of cartoon picture of the atom, and I'm not sure, but I would guess that you may have studied the Bohr model of an atom. One of the things you might learn about that model is that the orbital period, in other words, the time taken for an electron to whiz around, is about 150 attoseconds. So that's 0.15 of a femtosecond. So that is a really fast time, and it probably gives us an idea that somehow, if we wanted to look at those electrons, and I have to use the word look in quotes, you'll appreciate that we don't literally look at them, we would need something on that time scale. And so really attoseconds, which is the name of the time scale below femtoseconds, is what we need if we want to look inside atoms. Now, some of you might say, hey, Professor Tisch, that's a dodgy model. We know that the Bohr model is not really right. It's sort of a bit of a classical, semi-classical bodge. And in fact, you're absolutely right. But if you want a bit more detail, and I know that many of you, I know when I was studying at the equivalent of A level in Australia, I always liked that slide that showed a few things that I didn't quite know yet, and so something to sort of whet your appetite for more advanced studies. So in more serious quantum mechanical pictures, we think about the timescales in terms of a wave function which describes the system, and what we're interested in typically for looking at dynamics is so-called superpositions. In other words, we have a mixture of two, what we call eigenstates of the system, which are particular energy, sort of well-defined energy states of the system. And when we combine them quantum mechanically, as we've done here, we make a mixture of them, this leads to dynamics, it leads to motion. So don't worry if you don't get any of this. This is something to look forward to. Quantum mechanics is one of the most amazing things you study when you go on to uni to study physics. And what is well known is that the system in this superposition will undergo some kind of oscillations with a time scale. This is the important bit, which is given by Planck's constant divided by the energy gap between those states. So that's really the important thing to appreciate. And then we have to start thinking about what is this energy scale. And it turns out that in atoms, it can be of the region of 10 to say 100 electron volts, which means that the characteristic timescales are h divided by that, which is typically 40 to 400 attoseconds. So this connects nicely with the more simplistic Bohr model. And so when a scientist, a physicist is talking about an electron moving, what they're actually talking about is a wave packet, a quantum mechanical wave packet that is undergoing dynamics. And we can mentally think, well, the center of this wave packet is where we would imagine the classical electron. So that's the connection we make. I still think of electrons as classical little particles, but if I think a little bit more carefully, we think about these wave packets. Okay, so attosecond science, what is it? It's the study and control of attosecond timescale electron dynamics in atoms, molecules, and nanostructures. And the really key thing is that if we think that we've got a time scale which really is describing the dynamics of those things, that then really means that that's the time scale which all fundamental changes occur that are mediated by electrons. So pretty much all of chemistry and therefore biology is mediated by the way electrons move, and so this is the key time scale, the attosecond time scale. Now this is a busy slide. I don't expect you to be able to take it all in. What I want you to look at is that these are circles of time, starting from the very fastest going out, and right at the epicenter of this is attosecond time scales. And there are all of these fascinating physical phenomena that occur on different time scales. And the important thing to look at here is that by understanding what's going on these fastest timescales, we not only learn a great deal about basic science and physics, but we also have potential impact in a range of applications, from things called light wave electronics, so that's the next generation perhaps of computers that rely on optics and light, through solar energy, catalysis, understanding biomolecular function, lots of really interesting areas that this kind of research could impact into. So I've kind of tantalized you. I've said that to look at electrons we need to make attosecond light, and I've shown you that already the technology exists to make femtosecond light. How can we get into that attosecond regime? And just to remind you, 1 attosecond is 1 nanosecond. So that's 10 to the minus 18 of a second. Well, the history tells us something. So if we plot how short a laser pulse we could make against the year, you'll see that basically there was some good development. In other words, the pulse was getting shorter and shorter, and then they kind of reached a limit. And then there was this new generation of lasers known as titanium sapphire lasers, and they got shorter and shorter. Take note, this is a logarithmic scale. They got shorter and shorter, but they also seemed to run out of steam. And so there's this kind of brick wall here that we just couldn't get much below about 1 femtosecond. And the reason for that is very fundamental. At around 1 femtosecond, the light pulse duration is approaching the optical period of the underlying light wave. And you just cannot have a pulse that propagates in the normal sense that is shorter than the period of the light. So this is a fundamental limitation, and it probably would get you thinking that if we want to go shorter, we need to have basically a shorter period of the light, in other words, a higher frequency. So the key enabling technology was to be able to make lasers which have much higher frequencies than the previous generations. And to do that, we can use something which connects a little bit with what we heard in the excellent previous talk. We can focus one of these very high intensity lasers that we heard about into gas. We can kind of make a plasma as well. And what comes out of that is X-rays, bursts of X-rays. And those X-rays actually are a result of all of the little atoms in there basically being excited by this very strong laser and then being forced to emit their own light in the form of X-rays, which basically leave the sample. And because there's very many of those, the light that comes out can actually be quite strong, and it has a certain property known as coherence. In other words, all of the waves are sort of oscillating in phase. And this is a really interesting analogy to an accelerator, insofar as that what is happening at each of these individual atoms is very much like an atomic scale particle accelerator, that we have a strong field that we heard about before accelerating a charged particle. And in this case, the charged particle is basically forced to come back to where it started and release its kinetic energy as an X-ray. And just to have a quick look at how that process works, so you might recognize this shape. This is the potential that an electron sees in an atom. It's the binding potential. When we apply this very strong laser field, shown by this yellow curve, we can actually distort the atomic potential to the point where the electron can actually escape temporarily. And this is sort of like an ionization, but it's sort of like an ionization on a spring, in the sense that the electron is forced to come back because the electric field of the laser is oscillating, and when it does, it can recollide with the ion. And when it recollides with the ion, it gives up its kinetic energy in the form of a photon as it drops back down to the ground state. And this process is getting repeated in this laser field in trillions of atoms, and this results in these bright bursts of light. And it turns out that those bursts of light actually have sub-femtosecond duration. And the reason for that is that the electron escapes in a really short amount of time, and also when it comes back, it's moving so fast and the ion core is so small that that is also a very brief encounter, and this leads to these very short pulses of light. Now, a little bit of history. Back in 1992, there were two Hungarian scientists, Farkas and Toth, who were looking at the light spectrum that you get out from this process that I just mentioned. And they were scratching their chins and they said, actually, this reminds us a lot of the light spectrum that we get out of one of these femtosecond lasers. It consists of these frequency spikes. And they made a very telling, so that's what you get out of a laser, a regular femtosecond laser. And this is the emission that you get out of this so-called high harmonic generation process that I just spoke about. And they said, look, this looks pretty similar. And they wrote a really important paper which they predicted that if you did things just right, then maybe, because of the fact that these are much higher frequency, we could break through that brick wall and we could make pulses which were on an attosecond time scale. And it took a little while, about 5 years, and this is the way science goes. Some theoreticians will make some predictions, and then experimentalists eventually will test those, or vice versa. Experiments will yield results that theoreticians have to then try to explain. In this case, the theory came first, and in 2001, the first demonstration of that emission was actually done in France, and the details are a little bit complex to go through in a short amount of time, but the point was that these scientists made, using a femtosecond laser to drive this X-ray production process called high harmonic generation, they made a train of attosecond pulses, the very first time in the world that anybody had made light pulses which were less than a femtosecond in a chain of pulses. And this, these trains of pulses have some really interesting applications. They can be used in a manner analogous to like a strobe photograph. So this is somebody serving with strobe photography, and actually this is now a strobe photograph of electron wave packet motion in an atom that was done using these brief pulses of light. So it has fulfilled its promise in the sense that we're now able to make the movies of those electrons that I was talking about before. Now, that was a technology that makes these pulses in a chain, what we call a pulse train. And in parallel, people were starting to develop techniques to make those femtosecond lasers, which were at the start of the story, even shorter. And this is something that we do in my lab on a routine basis now. We take one of these laser pulses and we pass it through an optical system that basically makes it shorter. And what's really cool about this is that it takes a laser and actually turns it into a white laser. Many of you, when you think about a laser, will think a laser is a particular colour. You probably played around with helium neon lasers at 632 nanometers. But in this process, we make a laser which actually becomes almost white. And that, as you will all know, this picture doesn't really do it justice, but this beam is closer to white when you see it. And that means it has a huge range of colours in it. And so this is far from a monochromatic source. And indeed, it's this property that makes these pulses really short. And the reason that we got interested in doing this was that in 1997, so again before the first measurement of those trains of pulses, other scientists now in the US had worked out that if you could make your femtosecond pulse really short that was used to generate those high harmonics, then rather than having a train of these attosecond pulses, you might be able to just make one per laser shot. And that turns out to have many advantages in terms of measurements. And that required another technological pillar. So the story here is just to show you that many different things have to come together for these kind of scientific achievements. And so what people had to work out how to do is to take a laser pulse, which normally has this funny property that as you look at it, as it propagates, it's going to change its wave position relative to the pulse envelope. And these guys who got another Nobel Prize now for this technology, they worked out a way of building a laser system, you can see it's pretty complicated, which enabled scientists to lock that motion. Because that scrolling motion through that we can see here, which is a property of a very short laser pulse, is actually a real pain in the neck when you want to try to generate attosecond pulses. And so they developed a technology to stop that happening. And the important thing is that when you generate these high harmonics with a pulse where this is stabilized, you get these nice sharp spectral fringes that we saw before, which are a real requirement for what we want to do. So how on earth do you measure the shortest pulse ever generated? There's this old adage that if you want to measure something short, you need something even shorter. What if you've already got the shortest thing? Well, this is a real conundrum. And something that we can use is known as attosecond streaking. And this is a little bit technical, but hopefully it'll challenge you to think a little bit about what's going on. So what we try to do is we try to use electrons again to measure the the shortness of the pulse. And so what we do is we fire, and there's a little animation that comes here, we fire our very short pulse that we want to use into some atoms. That very short pulse pretty much instantly produces an ionization event, releasing an electron into this very strong laser field. Now, the very strong laser field, as we heard in the previous talk, will accelerate that electron, and it basically wiggles it. And so here's our little wave packet that we introduced. And what's going to happen is that that electric field of that strong laser is going to wiggle it up and down. And we're going to detect those electrons here. And so as you might imagine, when they are wiggled in the upward direction, we're going to see an increase in their kinetic energy. And when they're wiggled in the downward direction, we're going to see a decrease. So what this means is that when we repeat this experiment, changing the timing of these two pulses, we get this oscillation in the measured kinetic energy of the electron. And that oscillation, this picture, which is called a streaking trace, contains the information about how short that pulse is. Now, probably everybody in the audience has a different connotation of what streaking means. And I have to say there was a little bit of confusion with the German postdoc, but we did manage to stop him before there was any embarrassment. Now, so the story continues. So using these techniques, the locking of this scrolling behavior, finally, we got what are called isolated pulses. So not pulses that come in groups, but just one per laser shot, which, as I said, is an important requirement for many experiments. So back in 2001 was the first observation of a pulse which was 650 attoseconds. In 2004, that was reduced to 250 attoseconds. So you can see here the width, and you can see here these streaking traces, obviously improving as time went on. And one of the other amazing features of this is that this technology gives you a method to measure the direct electric field of a light wave. Maybe now, or maybe in first year university, you might even have lecturers that say that you cannot actually really experimentally measure the instantaneous electric field of a light wave because it's oscillating too fast. And we normally think about time-averaged quantities like the intensity and so on. But actually, this technology breaks that old way of thinking, and we can actually measure now the electric field of a light wave, which is oscillating at something like 10 to the 15 hertz. So this is a really new feature of this kind of technology. So you might be wondering, where is the current world record? The current world record now, which was held currently by a group in Florida, is 53 attoseconds. Just to put that into some context, that's about the amount of time that light takes to cross a virus. So this is a very, very short time. This is the shortest controllable event in science. And here's the data, which obviously you need to produce if you want to publish that result, as my colleague Zhenghu did. So the progress can continue. The story is shorter. Who knows where it's going to go, where you guys perhaps may be involved. Push it through to the next time domain. Anybody know what the one below Atto is? I'll give somebody a fiver if they know, who's not a scientist. Attosecond. Okay, so let's have a quick look in my finishing slides at what an attosecond laboratory looks like. So this is my laboratory at Imperial College in London. I encourage anybody who's thinking about studying physics to at least have a look at what we do at Imperial. This is in the lab, which we call 007. It sounds really Bond-esque, but actually it's just the name of the number of the lab. So you can see a lot of equipment, a lot of hardware. We have all kinds of different apparatus. And basically what we are able to do with these systems is to make now what we would like to think of as an attosecond camera. So going back to the earlier slide, what we actually have now is this kind of time resolution on that shutter. And I think my time is basically up now. So on that note, thank you very much for your attention. I realise that I've probably pushed you a little bit in terms of your knowledge, but I wanted to do that intentionally because I know that the really exciting thing for many of you is to go to the next step, and you're probably already beginning to get frustrated with the physics that you're learning at the moment, and probably many of you are reading books trying to get that extra information. So I thought I wouldn't patronise you by kind of giving a too easy talk. I wanted to have some of the detail there, and hopefully that will inspire some of you perhaps to have a little bit of a look at some of these details in the future. So thanks again for your attention.